Hello everyone and welcome back to another mini concept, this time on rate laws. So as I mentioned in the last video, there are actually two ways to describe the rate of reaction. One is through the rate expression, which involves the change in a reactant over a change in time. Now this time, we're going to be talking about a mathematical way to determine the relationship between how concentrated a certain reactant is, or what the concentration of a certain reactant is, and how it changes the rate of the reaction. As I mentioned in the last video, concentration is a factor that changes the rate of a reaction, and if we increase the concentration, it should get faster. If we decrease the concentration, it would get slower. So this is a mathematical way of describing that as a factor in how fast or slow a reaction occurs. So before we get into anything, we have to first understand what this set of data is. This is quite math heavy, however at the same time it's really just observation heavy. So let's try seeing that now. These are all experimental data. And why is it experimental data? Well, it's because A and B could react, right? They could react. However, based on what we know, based on what data we have, these are the rates that we obtained, or these are the rates that's given. And why is it important that we use experimental data? It's so that we know that in a controlled environment, only A and B are reacting. Let's say that A and B appear naturally. Well, they would be mixing with other they could possibly mix with other elements, not yield what we're looking for. So experiments are the most controlled way of us getting our data on how a reaction between A and B would go. That's just for extra understanding, right? Now another thing to take note of is that these are all different trials. So this is trial 1, trial 2, and trial 3. These are sets, so these are all linked together. Alright, and now let's get on to the solving. So like I introduced in the last video, a rate law is given by the rate is equal to K, the rate constant, times the concentration of reactant A to the power of M, that's the concentration of reactant B to the power of N. Now, how does this work? So here we can actually draft it already, and we already did, simply because we don't know what K is and we don't know what M and N is. So how do we get M, N, and K? Well, that's actually what we're looking for here. So we have to identify the orders of the reactants, which are M and N, and the rate constant K, as well as create the overall rate law. So the overall rate law would include K in what I want to show you guys now. Sometimes it doesn't specify you have to put K, sometimes just K with the reactants having their orders. So how do we do this? How do we get M and N? So before anything, we need M and N because it's impossible to derive the rest without it. Or even if it were possible, it's extremely difficult. So let's start with reactant A. So reactant A is present in all 3 trials, and we want to see or describe the effect of concentration. Obviously, if we want to see the effect of concentration of A, we need it to change, right? So we need to look here for a reaction, or we need to look for a pair of trials of the reaction where reactant A changes. So here we can see that in trial 1, reactant A's concentration is 1.5 molar, while in trial 3, its concentration is 3 molar, and in trial 2, it's also 1.5 molar. However, between these 3, So there are changes between 1 and 2 and 3. So 1 and 2 are the same, however it changes at the third trial. Now here, during the reactants the reactants of trial 1 and C are the same, while in trial 2 it changes. Why does that matter? Well, we want to isolate the relation of the change of rate to only one reactant. So we need to look for a pair of trials where only reactant A's concentration is changing. So since here trials 1 and 2, trial 1 is the only one between trials 1 and 2. Trial 1 is the only one that has the same concentration of B as trial 3. So we cross out trial 2 just for reactant A. So that means the pair of trials that we're going to be using are 1 and 3. So we can try now to draft the rate laws. And to solve for the order, we do this format of solving. So we have the rate law of the second equation over the rate law of the first equation. Now, how do we know which one is the second and first? Standard way of solving for it would be to just have whichever one has a greater value be put on top. So for this case, this would be trial 3 on top over trial 1. So how would this look like? This would look like this. So let's use the purple pen. So again, trial 3 over trial 1. So the rate of trial 3 is 6.40 times 10 to the power of negative 1 over 3.20 times 10 to the power of negative 1 is equal to K times 3.00, no brackets rather, sorry, 3.00 to the power of M times 1.5. Let's move this to the left. Times 1.50 to the power of N. This is based on trial 3. Now, the bottom side would be K times 1.5 or 1.50 rather to the power of M and 1.50 to the power of N. So, now, what do we do from here? Well, we're just going to simplify both sides. And actually, the mathematical reason why we need to have reactant B have a constant concentration when solving for the order of A is so that we can actually cancel them out. So if you look here, 1.50 to the power of N cancel out, the K's cancel out. So we're going to simplify our overall equation. So this is equal to 2. Right? This will cancel out. And 6.4 divided by 3.20 is just 2. And 3 over 1 3 to the power of M over 1.50 to the power of M is the same as 3.00 over 1.50, all to the power of M. We would distribute the M's. So this is actually just equal to 2 to the power of M. Now, when 2 is equal to 2 to the power of M, how do we get M? Well, clearly we can see here that it's going to be equal to, M is going to be equal to 1, because 2 to the power of 1 would be 2. However, we can actually use logarithms here. So an easy way would just be to apply common log. So common log would look like this. So just apply on your calculator log 2 and then log 2m, log 2 to the power of m. Now log 2 to the power of m is also equal to m times log 2. So this would bring us to isolate m, we would be getting log 2 over log 2 is equal to m, which is also equal to 1. And that's it. So the order of reactant A would be 1. So let's get rid of this now. So now we know that M is equal to 1. So in our rate law, we're just going to replace M now, and we're going to put 1. Alright, so now that we got that, let's go solve for N in a faster manner. So let's just breeze through this a little bit. So we're going to reset here. If you want to go back to it, please, I invite you to replay that part of the video. Alright, so now we're looking for reactant B, the order of reactant B. Okay, so the order of reactant B, we have to look for, again, a set of trials where only B is changing while the concentration of A is the same. So here we can see between 1 and 2, concentrations of A are the same. So that's what we're going to be looking at first. And the concentration of B is actually also changing. So that this could actually be the rate that we're going to be using. So we're between trials 2 and 1. Trial 2 has a greater value for B. So we're going to be putting that on top. So the value of trial 2 for its rate is 3.20 times 10 to the power of negative 1 molar per second, and over 3.20 rather, sorry, 3.20 as well, times 10 to the power of negative 1. Now on the right side, we'll be having the rate law. So that's 1.50 to the power of 1. Because now that we know what M is, we can just put 1 times 1.50 to the power of N over, or rather, times 2.50, sorry, to the power of N over K times 1.50 to the power of 1 times 1.50 to the power of N. So again, these will cancel out. The K's cancel out, the 1.50s cancel out, and we're left with, this is going to be equal to 1, and this is going to be equal to 2.50 over 1.50 to the power of N. So this is going to simplify to, well, actually it doesn't really matter what it simplifies to, because based on the law of logarithms, any number raised to the power of 0 would yield 1, right? And we're really not looking for the answer to 2.50 over 1.50. Instead, we're just looking for what is the exponent that will make whatever quantity in here equal to 1. And if you put this in your calculator, if you use the logarithm as well, like we did earlier, we will find that N should be equal to 0. Again, the longer version of this would just be log 1 is equal to N times log of whatever 2.50 over 1.50 is. And we would get log 1 over log 2.50 over 1.50 is equal to N. Now log 1 is equal to 0, and any number 0 divided by any number is equal to 0. So N would be equal to 0. So I highly suggest for this topic, review how log works, the properties of logarithm. But that's basically it. That's actually pretty much all you'll need to know for logarithms regarding this topic. So now we know that the value of N is actually just 0. So now let's get rid of all of this. And what does it mean when we have 0 as the order? There. So before we get into that, let's simplify this actually. So our rate will now be our final rate law. Our final rate law is going to be the rate is equal to K times the concentration of A raised to 1. Now, why did we not include B? Well, it's because B raised to 0 is just 1. And that's actually what I'm about to explain now about zero order reactions. So B, the order of B is zero order. Now, what does that mean? A zero order reaction means that regardless of the concentration of a certain substance, the rate of reaction will always be the same. So no matter how much I put of B, the rate of the reaction will still be the same. I can put 6 tons of B and nothing would change. On the other hand, if I put 6 tons of A, something would change. I hope that's clear. Now, how about the overall order? Now, it's not asked here, but the overall order of a reaction, overall order, is given by M plus N. And, well, actually, it's not just N, because sometimes you can actually have more than just this. Sometimes you'll have 3 reactants, or 4 maybe. But basically, it's just the sum of all of the exponents. So in this case, it's 1 plus 0. So the overall order of the reaction is first order reaction. Alright, so now how does a first order reaction go? Well, a first order reaction is more explainable by its integrated rate law. So now let's actually enter that topic. So we're going to clear out this set of like words. I'm gonna remove this, and we're just going to keep our rate law for this one. So there are 3 primary integrated rate laws. So there are 3 integrated rate laws because there are 3 primary orders. So there's zero order, there's first order, and there is second order. Now, zero order, this rate law is, well, all of these are linear expressions. So all of the following equations I'm going to be giving are actually in the form of y equals mx plus b. Because on a graph, they would be showing this, or they could be showing this. Okay, so for a zero order reaction, our formula is the final concentration of any reactant is equal to the negative rate constant times the time or the duration of the reaction plus the initial concentration. Now for the first order, the final the equation is quite the same. However, instead of this, it's going to be applying the natural log of the concentrations of each. Oh, sorry, I accidentally wrote null here. It should be F. So there. It's going to be the exact same. However, this time we apply natural log to our concentrations. And now for second order, it's just going to be the reciprocal of the concentrations. So we have 1 over the final concentration of A plus KT. Okay, now this time K is no longer negative, plus 1 over the initial concentration of A. Now what do the graphs of these look like? Well, for this, these would generally give downward graphs, while this would give an upward graph. Okay. There. Now these graphs, it's important to note that this is when we plot our y values versus time. Okay, so now what do we do with these? Well, these reactions, right? Every reaction has an overall order, and the overall order will describe will determine which rate law we're actually going to be using, which integrated rate law we would use. So based on this, our overall order is 1. So for this rate law, we'll actually be using the first order integrated rate law. So take a screenshot of this, or you can rewind the video because I'm just going to put this up here. Alright, so now let's say that we're going to solve for the initial concentration. The initial concentration of reactant A. If the final concentration is equal to 0.5 moles, not moles, rather molar. Now we also need K and we also need T, but actually we haven't solved for K, so let's give that a try. Now, since we already know what the overall rate law is, we can actually just pick any equation here, any trial here, and then just plug in the values so that we can see what our rate constant is. So for this one, let's just keep it simple. Just pick any of this, and we'll probably use just trial 1. So trial 1, the rate would be 3.20 times 10 to the power of negative 1. And this is equal to K times 1.50 to the power of 1, or just 1.50. So to derive for K, we would just need to divide 3.20 times 10 to the power of negative 1 over 1.50. And using our calculator, hold on. Using our calculator, we would get 0.320 divided by 1.5 is equal to 0. K is equal to 0.213333333333. Now, what's the units of our rate constant? Well, the rate constant is always going to be in terms of n to the power of 1 minus n times seconds to the power of negative 1. What does this mean? So n here is the overall order. So our overall order is going to be 1, right? So let me move this. Our overall order is 1, and so our final unit for our rate constant would thus be equal to 0.213 m1 minus 1 is equal to 0 times s to the power of negative 1. So this means that our final answer for our rate constant is 0.213 per second. Now, it might seem strange. Why is there nothing on the top? Well, that's it. More explanation on this perhaps in the next video. But this is essentially it. It makes more sense when we compare the equations based on their half-lives. It's actually a lot easier to explain when we compare them against their half-lives, but that's for another video. So now we know our K is equal to 0.213 per second. So let's put this up here. Oops. If I can just make that hello. Okay, there. So our K is equal to that. Now let's say our time here in this problem would be equal to 60 seconds. What we're looking for? Find the initial concentration of A. Alright, so we know that our order of reaction here is 1. So we're just going to lay out our integrated rate law. So our integrated rate law is the natural log of the initial concentration of the final concentration rather is equal to the negative rate constant times time plus the initial the natural log of the initial, rather. Natural log of the initial concentration. Now, how would we get the initial concentration from here then? Okay, well, easily we can just transpose and isolate it. So our formula would thus become natural log of the final concentration plus the rate constant times time. And this would be equal to ln A initial. So now let's try plugging in our values. So plugging in our values here, let's use the blue pen. So you would have the natural log of 0.5, not brackets, rather just here the parenthesis, plus 0.213, 0.213 times time, which is 60 seconds, is equal to the natural log of the final answer, which is our initial concentration. So try putting this in your scientific calculators and see if we get the same results. So ln 0.5 is equal to negative 0.69 or 693 there, and we add this to 0.213 times 60. So that would be 0.213 times 60 is equal to 12.78. This is equal to the natural log of A, which is, based on our solving, it would be 12.087. So now, this is just the natural log of A. In other words, this answer, right? This answer is just the exponent of E. So this answer is just the exponent of E. Now, how do we get A? So to get A, or the initial A, all we have to do is just raise E to the ln of A initial, which is this, what we just solved for. So in other words, what all we have to do now is just find E on our calculator and raise it to the power of 12.087. And this would be equal to E raised to 12.087. 1.77 times 10 to the power of 1, 2, 3, 4, 5. 5 molar. Quite a large number. However, that's it. So I hope that makes sense.